Import-export control refers to the ability of a distributed generation system to adjust its power flow between the grid and the local load. This control mechanism is essential for ensuring grid stability and optimizing the utilization of distributed generation systems. In a distributed generation utility parallel system, power flows can occur in multiple directions. Firstly, import, where power is drawn from the grid to supplement the local load. Secondly, export, where power is generated by the distributed generation unit and sent to the grid. Thirdly, bidirectional flow, where power flows in both directions, depending on the load and generation profiles. Import-export control enables distributed generation systems to maintain grid stability by regulating the power flow between the grid and the local load. Distributed generation systems can prevent voltage and frequency excursions that could destabilize the grid. Optimize distributed generation utilization by adjusting power flows based on load demand and generation availability. Distributed generation systems can maximize their contribution to the grid while minimizing grid reliance. Comply with grid interconnection requirements. Most utilities require distributed generation systems to have import-export control capabilities to ensure grid protection and interoperability. Import-export control is typically achieved through electronic devices called inverters or frequency converters. These devices regulate the voltage and frequency of the power flowing to and from the grid, allowing for precise control of power flow direction and magnitude. The benefits of import-export control include enhanced grid stability, optimized distributed generation utilization, reduced grid reliance, improved power quality, lower operating costs, and increased renewable energy integration. Let's delve deeper into the technical aspects of import-export control within distributed generation utility parallel systems. The core function of import-export control is to manage the bidirectional power flow, ensuring that the distributed generation unit operates in harmony with the utility grid. This is crucial because uncontrolled power injection or withdrawal can lead to voltage fluctuations, frequency deviations, and even equipment damage on the grid. Inverters, as the primary interface between the distributed generation source and the grid, play a pivotal role in this control. Modern inverters are sophisticated devices that not only convert direct current power from sources like solar panels or batteries into alternating current power compatible with the grid, but also incorporate advanced control algorithms. These algorithms constantly monitor grid parameters such as voltage, frequency, and phase angle. Based on these measurements, the inverter adjusts its output to either import power from the grid, export power to the grid, or maintain a balanced state where it only supplies local loads. Consider a scenario where a solar panel system is connected to the grid through an inverter. During peak sunlight hours, the solar panels generate more power than the local loads require. In this case, the inverter, under import-export control, will export the excess power to the grid. The amount of power exported is carefully regulated to avoid exceeding the grid's capacity or causing voltage imbalances. Conversely, during periods of low sunlight or high local demand, the solar panels may not be able to meet the entire load. The inverter will then import power from the grid to supplement the solar generation, ensuring that the local loads are always adequately supplied. The control algorithms within the inverter typically employ several techniques to achieve precise power flow management. One common technique is power factor control, which ensures that the current and voltage waveforms are in phase. Maintaining a unity power factor minimizes reactive power flow, which can strain the grid and reduce its efficiency. Another technique is voltage regulation, where the inverter actively adjusts its output voltage to maintain a stable voltage level at the point of common coupling with the grid. This prevents voltage sags or swells that could affect other connected equipment. Frequency regulation is also crucial, especially in islanded microgrids where the distributed generation system is operating independently of the main grid. The inverter must maintain a stable frequency to ensure that all connected devices operate correctly. To comply with utility interconnection requirements, many distributed generation systems are equipped with sophisticated protection functions. These functions automatically disconnect the distributed generation unit from the grid in the event of a fault or abnormal condition. For example, If the grid voltage or frequency deviates outside of acceptable limits, the inverter will trip offline to prevent further disturbances. Similarly, if a fault occurs on the grid, such as a short circuit, the inverter will disconnect to protect itself and prevent it from feeding fault current into the grid. Communication between the distributed generation system and the utility is also essential for import-export control. Many utilities require distributed generation systems to be equipped with communication interfaces that allow them to remotely monitor the system's performance and control its output. This communication can be used to implement advanced grid management strategies such as volt-VAR control, where the utility can adjust the inverter's reactive power output to improve voltage profiles on the grid. The implementation of import-export control also involves careful consideration of the grid's capacity and limitations. Utilities typically conduct detailed studies to assess the impact of distributed generation systems on the grid before allowing them to connect. These studies evaluate the grid's ability to handle the increased power flow and ensure that the distributed generation system will not cause any adverse effects. In some cases, the utility may require upgrades to the grid infrastructure, such as new transformers or transmission lines, to accommodate the distributed generation system. The economic benefits of import-export control are also significant. By allowing distributed generation systems to export excess power to the grid, owners can earn revenue and offset their energy costs. This can make distributed generation systems more financially attractive and encourage their adoption. Furthermore, by reducing reliance on the grid, distributed generation systems can improve energy security and reduce vulnerability to grid outages. The integration of renewable energy sources, such as solar and wind, is greatly facilitated by import-export control. These intermittent energy sources can be seamlessly integrated into the grid without compromising its stability or reliability. The inverter's ability to regulate power flow ensures that the grid can handle the variability of renewable energy generation. In summary, import-export control is a critical technology for enabling the widespread adoption of distributed generation systems. It ensures grid stability, optimizes distributed generation utilization, and provides numerous economic and environmental benefits. As distributed generation continues to grow in popularity, import-export control will become even more important for maintaining a reliable and sustainable energy system. Now let's discuss the specific electronic devices employed to achieve import-export control, focusing primarily on inverters and frequency converters. As mentioned before, inverters are the workhorses of distributed generation systems, converting direct current power to alternating current power suitable for grid connection. However, modern inverters are far more than simple direct current to alternating current converters. They are sophisticated power electronic devices that incorporate advanced control, protection, and communication features. The core of an inverter consists of semiconductor switches, typically insulated gate bipolar transistors or IGBTs, or silicon carbide metal oxide semiconductor field effect transistors, or silicon carbide MOSFETs, which rapidly switch on and off to create an alternating current waveform. The switching frequency is typically in the kHz range, allowing for precise control of the output voltage and current. The inverter's control system uses feedback from sensors that monitor grid voltage, current, and frequency to adjust the switching pattern and maintain the desired output characteristics. The control algorithms are often implemented using digital signal processors, or DSPs, which are specialized microprocessors designed for real-time signal processing. The inverter's protection functions are essential for ensuring safe and reliable operation. These functions include overvoltage protection, undervoltage protection, overcurrent protection, and frequency protection. If any of these parameters deviate outside of acceptable limits, the inverter will trip offline to protect itself and the grid. Anti-islanding protection is another critical function that prevents the inverter from continuing to operate and energize in a portion of the grid that has been disconnected from the main power source, a potentially dangerous situation. In addition to inverters, frequency converters are also used in some distributed generation systems, particularly those that involve rotating machines such as wind turbines or microturbines. Frequency converters are similar to inverters, but they also perform a frequency conversion function. This is necessary when the distributed generation source produces power at a frequency that is different from the grid frequency. For example, a wind turbine may generate power at a variable frequency depending on the wind speed. A frequency converter can convert this variable frequency power to the fixed frequency of the grid, typically 50 Hz or 60 Hz. Frequency converters typically use a direct current link to decouple the input and output frequencies. The input power is first converted to direct current, and then the direct current power is converted to alternating current power at the desired grid frequency. This allows for independent control of the input and output frequencies. Like inverters, frequency converters also incorporate advanced control, protection, and communication features. They are essential for integrating distributed generation sources that produce power at variable frequencies. The choice between using an inverter or a frequency converter depends on the specific characteristics of the distributed generation source and the grid interconnection requirement. In many cases, inverters are sufficient for connecting direct current sources such as solar panels and batteries to the grid. However, frequency converters may be necessary for connecting rotating machines or other sources that produce power at variable frequencies. The design and implementation of import-export control systems require careful consideration of several factors, including the grid's characteristics, the distributed generation source's characteristics, and the applicable regulatory requirements. Utilities typically have specific interconnection standards that must be met before a distributed generation system can be connected to the grid. These standards specify the technical requirements for import-export control, protection, and communication. Compliance with these standards is essential for ensuring safe and reliable grid operation. Furthermore, the performance of import-export control systems must be continuously monitored and verified. Utilities often require distributed generation system owners to provide regular reports on their system's performance. These reports may include data on power generation, power consumption, and grid interactions. This data is used to assess the system's impact on the grid and ensure that it is operating within acceptable limits. In conclusion, the electronic devices used for import-export control, primarily inverters and frequency converters, are sophisticated power electronic devices that play a critical role in enabling the integration of distributed generation systems into the grid. These devices incorporate advanced control, protection, and communication features to ensure safe, reliable, and efficient grid operation. As distributed generation continues to grow, the importance of these devices will only increase. Finally, let's explore the various benefits associated with import-export control in distributed generation systems. These benefits span several areas, including grid stability, distributed generation utilization, grid reliance, power quality, operating costs, and renewable energy integration. Enhanced grid stability is one of the primary benefits of import-export control. By regulating the power flow between the distributed generation system and the grid, import-export control helps to maintain a stable voltage and frequency in the grid. This prevents voltage sags or swells and frequency deviations that could damage equipment or disrupt grid operation. Import-export control also helps to mitigate the impact of intermittent renewable energy sources on the grid. By smoothing out the power fluctuations caused by solar and wind generation, import-export control makes it easier for the grid to absorb these resources. Optimized distributed generation utilization is another key benefit. Import-export control allows distributed generation systems to operate at their maximum efficiency by matching power generation to local load demand. This minimizes waste and maximizes the economic benefits of distributed generation. By exporting excess power to the grid when local demand is low and importing power from the grid when local demand is high, distributed generation systems can optimize their energy consumption and reduce their overall costs. Reduced grid reliance is a further advantage. Import-export control allows distributed generation systems to reduce their reliance on the grid by generating their own power locally. This improves energy security and reduces vulnerability to grid outages. By reducing the demand on the grid, distributed generation systems can also help to defer the need for costly grid upgrades. Improved power quality is also a significant benefit. Import-export control helps to improve power quality by reducing voltage harmonics and other distortions on the grid. This is particularly important for sensitive electronic equipment that can be affected by poor power quality. By providing clean and reliable power, distributed generation systems can enhance the performance of other connected devices. Lower operating costs are an economic benefit of import-export control. By allowing distributed generation systems to generate their own power and sell excess power back to the grid, import-export control can reduce energy costs. This can make distributed generation systems more financially attractive and encourage their adoption. Increased renewable energy integration is a critical environmental benefit. Import-export control facilitates the integration of renewable energy sources such as solar and wind into the grid. This helps to reduce reliance on fossil fuels and lower carbon emissions. By enabling the widespread adoption of renewable energy, import-export control contributes to a more sustainable energy future. In addition to these direct benefits, import-export control also provides several indirect benefits. For example, it can help to create jobs in the renewable energy industry and stimulate economic growth. It can also improve energy literacy and promote energy conservation. The implementation of import-export control requires careful planning and coordination between distributed generation system owners, utilities, and regulatory agencies. It is essential to ensure that distributed generation systems are properly designed, installed, and operated to maximize their benefits and minimize their risks. Furthermore, it is important to develop clear and consistent regulatory policies to support the growth of distributed generation and promote its integration into the grid. In conclusion, the benefits of import-export control are numerous and far-reaching. From enhancing grid stability to reducing operating costs and promoting renewable energy integration, import-export control plays a vital role in creating a more reliable, sustainable, and affordable energy system. As distributed generation continues to evolve, import-export control will remain a critical technology for ensuring its success.